Okay, now 10:30 in JST. So I'd like to start this I²CNER seminar. Good morning and good evening, everyone. Thank you for joining the I²CNER seminar series. The I²CNER seminar series was launched in 2010 upon in the inception of I²CNER. Since then, the seminar series has featured the best researchers in the world on carbon neutral energy issues. I am I²CNER, a PI of multi-scale science and engineering for energy and the environment trust, and I will be your host today. Today, we welcome Dr. Mohammad Sarmadivaleh. I would like to briefly introduce him first. Dr. Mohammad Sarmadivaleh is an associate professor at Western Australian School of Mines, Minerals, Energy and Chemical Engineering, Curtin University. He has completed his PhD degree in petroleum engineering from Curtin University. He has extensive experience in research with a particular focus on underground hydrogen storage and geological storage of carbon dioxide. I asked him to speak today to share with us the latest research in underground hydrogen storage. There are researchers at I²CNER who is studying on hydrogen storage and transportation system, as you know, and he is one of the world's leading researchers on the technology to use underground reservoirs, such as depleted natural gas field, for hydrogen storage. This research is ongoing in Europe and the United States especially, and some practical projects are underway to store hydrogen underground. We are working together on this research now, and my PhD student who is studying on this topic is now accepted by him as a visiting research student and studied in Curtin University now. Now, I would like to invite our director, Professor Tatsumi Ishihara, to begin our session. Tatsumi, please. わかりました。Sorry. Now, still, he is not joining this meeting, so I'd like to skip the address from Tatsumi. Okay, before we begin, I would like to take a moment to remind you that your question will be addressed after the presentation. Please use raise hand, okay, raise hand button, or type your question, comment in the Q&A box you can find on a Zoom screen. So when you are called on, please unmute yourself. And this webinar will be recorded and made available on the I²CNER website. Okay. Tatsumi sensei, noted. Okay. I'd like to start. Okay. I'd like to start the presentation from Mohammad sensei now. So now, everyone, please welcome Dr. Mohammad Sarmadivaleh sensei. Thank you very much. Please go ahead, your presentation.
Let me share my screen.
Yes, please.
So, can you see my screen now?
Yes, we can find clearly. Please, yes, please, slideshow, yes.
Okay.
I can find your slideshow clearly, and also I can hear your voice clearly. So please start. Okay. Thank you.
Good morning and possibly good afternoon for some of us, ladies and gentlemen. Thank you very much for having me here. As you mentioned, I'm working on hydrogen underground storage as well as the CCS, geomechanics and metallurgy aspects of it. Today, I want to share my view of underground hydrogen storage and basically have an overview of the whole concept, plus some of our experimental results that we had recently, and would like a discussion with you to see what you possibly think of the technology future and how we proceed with that one. I need to acknowledge the work of my colleague in Curtin University, CSRO, and ECU, which basically forms the underground hydrogen storage hubs, and as well as my collaborator in Kyushu University in Japan and King Fahd University, that this work is not mine or my team work only. It's basically a collaboration between many of the parties. Okay. Everyone knows why we are moving from fossil fuel and start to investigate renewable as the future energy supply for the world. Problem with fossil fuel are very obvious with global warming and all of the environmental and geopolitical issue that we can face every day, especially with the war in Europe. So it's some going toward this renewable is a must, but there are inherent problems with this renewable. So when we want to replace solid and mainly solid and liquid forms of the energy carrier to something different, we need to change the infrastructure. We need to consider how current infrastructure can be used, and that's a big challenge. So if we look at, for example, how energy gets supplied and what the demand may look like, sorry. What the demand look like, this current board. I'll give you a few examples here to solidify the point, and most possibly all of you are aware of these examples. The graph, the graph in top left shows the demands in usually the sort of demand we have in Northern Hemisphere. This example came from the Europe. You can see in January, February, November, December, the demand is peaking. And somewhere in July, the demand goes down for heat. But problem is, for example, this sort of demand is completely opposite in Australia, in Southern Hemisphere, because now we are in winter and majority of you guys are in summer. But if you look at the supply of the solar and wind in Europe, is not consistent with the shape of the demand. It's unpredictable in many of these cases, and that can be affected by a rainy day or some other factor. So we cannot basically address this demand with this supply the way that we used to turn on our power plant and provide electricity, for example, to the grid. We need to have a different way of doing it. This model, which came as an example from the Europe, talks about the whole year seasonal supply of the energy. But even if we look at daily supply of the energy, we have quite huge problems. This is the red line, and the blue lines are daily energy, average daily energy consumptions of a household in New South Wales. You can see different hours starting from midnight. The demand goes up and down in a household. If this household equipped with 1.5 kilowatt solar at the roof, or 3 kilowatt, the dash line is the 3 kilowatts. You can see the demands are this green line in the summer, and the supply is either the solid green lines or the dash lines. You can see this supply of demand, even in a daily basis, will not work properly. And consider that in Australia, many of these houses already have this solar panel. In daylight, we will pump thousands of these kilowatts in every neighborhood to the grid, and there is no use of these electricity. But before and after this period, we have a lot of deficiency in the grid in terms of supply. Okay, problem can be a bit more extensive, especially about the location that you want to do these green projects. In the left, you can see the map for the solar potential and wind potential of the Australia. So in the middle of Australia, which is almost desert everywhere, you have a very good potential for solar. And especially in the coastlines, you have good potential for the wind. But if you want to have a solar combined with wind project, renewable project, we can't just look at the potential. We need to look at infrastructure. The map in the right basically shows how these things all get combined together. Australia is a vast country or a small continent, and majority of the population is in a coast. So you need to have this supply where the demands of this population does exist. And plus, Australia is one of the biggest player of energy supply in the LNG and coal. And if Australia wants to stay as important as it is in current energy supply, Australia has to move to renewable in a way that they can supply green hydrogen or green ammonia or any other form of carrier in the future as well. So the ports are important. Railway, existing pipelines, roads, center of the population, access to fresh water, and these are the things that are important to make a positive, net positive value projects viable in Australia. If you look at the Europe or Japan, the model is completely different because the population concentration in those countries are so tight in compared to, let's say, Australia, that basically this map of the potential will be very different. Okay, before we start about underground hydrogen storage, I want to just emphasize some very important point about the hydrogen. Most possibly you are all already know about this one, but I want to stress on those, and I will use some of these points in my future slides. So hydrogen has a very high permeation and extremely high diffusion into the solids and other material. Hydrogen is 8 times smaller than methane, and its density is just 7% of the density of the air. It makes it very difficult gas to handle. Hydrogen has very low ignition energy, as low as 0.02 millijoule, and its fast detonation. Its volumetric range is from 4% to 77%, means that it almost always explodes. And that makes it very difficult to handle hydrogen for either a laboratory work that what we are doing or a commercial facility using or producing the hydrogen. Its flame is invisible and thermal radiation of this flame is low, which makes it difficult to detect. But its flame temperature is 2,200 plus. So makes it very dangerous things for the fire caused with hydrogen. Plus, in terms of the human safety, we need to be very concerned about the hydrogen because you know that human needs almost 20% of oxygen for breathing. If that level reaches to 0 to 3%, the death gonna happen less than a minute. So we need to be careful, but hydrogen is very good to displace the air because its density is so low, it quickly goes up and fill it from the top. If there is no way for the hydrogen to escape, it just quickly fills. And as I said, the density is low, it expands a lot. Let's say if the cylinder of hydrogen leaks and quickly can cause death. Is colorless, odorless, and tasteless. Makes it very difficult for the human to detect it, similar to other gas that possibly one of our senses, either visual senses or taste or color, seeing it basically can help to detect it. This graph here shows the wide range of explosive of the hydrogen. If you compare it with methane, propane, and gasoline vapor, you can see hydrogen is always tend to explode and makes it difficult to handle. In comparison, its ignition energy is 1 order of magnitude, more than 1 order of magnitude less than methane and propane and gasoline vapor. So putting everything together, this is a difficult element to handle. If you look at the storage possibilities, there are different ways to store it. This graph shows the density of hydrogen versus the temperature in Kelvin, and here in centigrade. The first way of storing hydrogen is to make it liquid. if you want to make it liquid and keep it in almost ambient pressure, you really need to cool it down. Cool it down as 20 Kelvin, which is requires very special equipment and is very energy intensive. You can keep it in the room temperature, but pressurize it to 700 bar, 250 to 700 bar. Although this is kind of way of storing it at high pressure tank at the surface, but again, you can't, even with that pressure, you can't store much of the hydrogen, because if you look at the density is around the 30. So in comparison, the density of supercritical CO2 is 0.6, 0.7, depending on pressure and temperature. So you can see this is 0.03 in comparison with CO2. You can pressurize it and cool it down at the same time. So you require high pressure. You can increase the density of the hydrogen up as high as 100, but you really need a huge pressure and very cold conditions, which makes it again very difficult to have. In comparison, if you want to look at underground hydrogen storage, the underground hydrogen storage is somewhere here, although the density is going to be low, but the temperature is around 50, 60 degrees that we have underground hydrogen storage. We usually don't go above it. I've seen a project on 70 degrees as well, but to my view, that's quite high for valuable hydrogen and make it vulnerable for any kind of other reactions when we go as high as 70. But if you look at hydrogen in comparison with the other energy carrier for energy density, hydrogen has high gravimetric energy density, means a kilogram of hydrogen has huge amount of energy. But it has low volumetric energy density, means that if you want to have 1 kilogram of hydrogen, you need to sacrifice a huge volume, and that's a problem with hydrogen. So even with high pressure, its volumetric energy density is still very low, and that makes hydrogen very difficult gas to store. Again, hydrogen has a very low solubility in water, which is a good point for underground hydrogen storage, because when it comes to contact with all kinds of the water, we don't expect much of hydrogen to get dissolved in the water. In comparison, you can say this is the CO2 in 60 degrees. Let's say this is the CO2, this solubility is half gram per kilogram of the water. When it goes to methane, we are 50 times less than that. But when it goes to hydrogen, it's one order of magnitude less than the methane, which is a good sign for us, and I explain why this is a good sign. If you look at diffusivity of hydrogen, hydrogen diffusivity is not as small, and usually 3 times more than CO2 and methane. But at the end of the day, because its solubility in water is low, that diffusivity in the water will not make that much of problem. And how it's helpful, I will explain later. So we can have this sort of electricity, the source of for making the hydrogen from many, many ways. We can use sun, hydroelectric, biomass, wave, wind, nuclear, geothermal, and even the hydrocarbon CCS. And we basically can do all of this sort of conversion of the electricity to hydrogen, but it still is very expensive. We haven't had a proper hydrogen storage, underground storage project yet, except for, if I'm not mistaken, to the best of my knowledge, there are 6 underground salt caverns for commercially storing hydrogen, 3 in UK, 3 in Gulf of Mexico, and the rest of project is pilot to see how things goes. In comparison, surface tank of hydrogen can hold 5 to 10 gigawatts per hour. When we go to hard rocks caverns, you can increase it to 10 to 30 gigawatt hours. If you go to salt caverns, you can the luxury of going up to 100 or 250 gigawatt hours. And finally, if you go to gas field, depleted gas field or aquifers, you can have it as high as 20,000 gigawatt hours. So this point, I want to highlight it in the next slide for having a comparison. Let's assume we want to store 6% of Australia annual energy use, which is 100 terawatt hours of hydrogen storage, in one of the possible forms in of hydrogen storage. We can have almost 500,000 kilometers of 1 meter diameter pipe with 85 bars at 20 degrees centimeter. So with that one, you can go around the world, I think more than 10 times. So this is huge infrastructure to store that much of the hydrogen. If you gasometers tank, which is their capacity is around 90,000 cubic meter, you need 341,000 of them. If you want to have it in liquid form, you need 3.5 million cubic meters of liquid hydrogen. And that's for the comparison, that volume is 500 football ball stadium with 10-meter height. This is huge. Salt cavern is the only one practice, only technique practice to store hydrogen, but for so basically storing that much of the hydrogen, you need 300, almost 400 of these salt cavern, which is massive project, which gonna occupy or use a big land for doing the infrastructure. But if we go to gas fields, a Malin gas field in Australia, half of the capacity of that gas field can hold this much of hydrogen. So let's say if you want to store 200 terawatt hours of hydrogen, that gas field can do it. So this is the massive underground storage capacity that does exist in almost everywhere. If you look at the aquifers are almost everywhere, and you can have this project viable in many places. I'm not saying all of the aquifers are suitable, but I'm saying that at least we have these aquifer a lot more, and we have these gas field already studied with a good distribution around the world, so that might be able to use those for hydrogen storage. Okay, this slide shows different techniques, which I don't want, to say we shouldn't use any of the other techniques. But what I want to emphasize, if you really want to go to terawatt hours of storage, you really need to go to long duration energy storage. And as I mentioned, the best long duration energy storage, which are available are aquifer, gas fields, and salt caverns. In comparison, if you want to have a single salt caverns, this one, you can see that can produce 10 million cubic meter per day. But the problem is this capacity is not much. And as a result, it cannot hold this flow rate for more than few days. We can increase the capacity by increasing the number of the salt caverns. But as I mentioned earlier, you end up with the case that you really need a lot of them. If you really want to store hydrogen in seasonal capacity, you need to go toward depleted gas reservoir and aquifers. That's what we basically provide the huge volume for hydrogen storage. Okay, so we talk about the good point about underground hydrogen storage. Now we want to talk about the challenges. Putting reactive hydrogen underground is not as easy, and the recovery of that hydrogen is a challenging task. So we have tons of these challenges that I want to describe in the future slide, but here I try to put all of them together. So the caprock might be issue in terms of the crack that we might have, the fault that we might have there. Hydrogen plume goes up and start to interact with other material, methane and CO2, and possibly some other gases which does exist in depleted gas reservoir. If it's aquifer, it will react with existing mineral, possibly react with existing mineral. We have the microbes there. If we are using a cushion gas rather than hydrogen itself, the mixing of the cushion gas is a problem. If we pressurize and depressurize this reservoir, the cyclic loading and stress we provide by decreasing and increasing the pore pressure may create some problem. Around the wellbore, cement might have the problem in terms of the reaction between the cement and the fractures and flaws which we have in the cement around the wellbore. It becomes more problematic when we deal with basically the reservoirs that have a lot of old valve. You know that old valve, the way that we design it in petroleum is not mainly to keep hydrogen underground. So majority of the leak and problem that we have in oil and gas world is for the wellbores. Wellbores are one of the bottlenecks for integrity of the reservoir, and especially if that one being used for hydrogen underground hydrogen storage. Okay, so in order to basically, in order to give a very good view, in one of the projects that I was involved with future energy export, me and other colleagues basically work on screening tools. That screening tools try to see what are the different parameters in terms of storage integrity, hydrogen conversion and contamination, storage performance, and economic assessment toward the hydrogen storage in underground production. Majority of this work is one of our postdoc, Dr. Zhang, who is working in CSIRO now. And the work was led by one of my colleagues, Sam here. This is a good piece of work, which basically we try to qualitatively talk about the risk associated with any of these parameters. So I go one by one and try to explore and describe what will be the effect of different parameters, let's say in storage integrity and the rest. Okay. So in terms of the storage integrity, what we are concerned is whether we can keep hydrogen there. So we look at the Caprock reservoir and look at the wellbore itself. In that regard, just please pay attention that what I'm looking for is to keep hydrogen there. So I want to have the integrity of whole storage. Diffusion of the hydrogen, wellbore problem, crack, faults, microbial activity, the effect of the cyclic of the hydrogen and brine rock interaction are the matter of the concern. If we go one by one, we can find a risk associated with all of them. I explained how we basically do it. We have the variables, we divide with primary and secondary in terms of their importance. Here we talk about caprock, reservoir, and the wellbore. These variables we try to the literature review and basically quantify what do we mean and what are the important part about it. We talk about its likelihood and consequences, and finally we try to show a risk for any of those variables. So if we start with geochemical reaction, this geochemical reaction may happen in a caprock reservoir around the wellbore. So there are minerals like carbonate, which some of the study shows that they will react. To my view, and the risk here is a medium, but to my view, carbonate is not a problem because mainly we need hydrothermal condition 250 degrees centigrade in order to activate those. So kinetic barriers and time scale will stop to see these things have a problem. I'm not talking about the combination of the, let's say, microbial and geochemical reaction. Geochemical reaction by itself shouldn't be a problem for the carbonate. If we have some minerals that iron-bearing minerals that might trigger some of these microbial reactions, then this is what we saw in the laboratory as well, that I will explain later on. But apart from those, geochemical reaction shouldn't be a problem for integrity. What I'm saying shouldn't be a problem, I'm talking about the geochemical reaction, basically doing these changes by itself. I'm not talking about basically it combined with microbial reaction activity or geomechanical parameters. Microbes are the one that we have this concern. We have mutagenesis, acetogenesis, and sulfur-reducing and iron-reducing microbes. They are the matter of concern for contamination, but in terms of integrity, they are not a problem. The only problem we can see in terms of integrity for the microbes are casing corrosions, facility corrosion with and hydrogen embrittlement. That can be a big concern. In terms of the integrity, microbe, to our view, doesn't play a big role. Fault and fracture, mainly geomechanical, is a very big concern. But if you look at the risks are medium to high in some cases. But you need to just consider that our knowledge and experience with geomechanical underground storage of the gas is vast. We have a very good capability in monitoring it with seismic monitoring, 4D seismic monitoring, microseismic monitoring, and recently we developed a very good knowledge around fiber optic sensing. And although this is a matter of concern that can kill the whole project, but our knowledge is very solid. So although the risk is high, but I would consider it as the least concern for underground hydrogen storage for the reason that we really know about this concept from the other CCS project and other underground hydrogen storage. I'm not saying that can be a problem. I'm saying that we know it very well. Hydrogen cycling can be a problem. Again, hydrogen cycling can trigger some geomechanical reaction, especially about the faults. If you have high injection rate, we might create some fracture around the wellbore. If you have low bottom hole pressure or high bottom pressure, that can cause perforation collapse or creating some fracture. This can be a problem, but again, our knowledge about it is very solid. Second topic I want to talk is basically contamination and conversion of the hydrogen. So in this case, the biggest problem comes from the microbes activity. Geochemical and gas mixing can contribute into that one as well. So before I go to show the screening tool for those parameters, I want to emphasize what sort of microbe do we have underground and how they perform. So we have metagenesis, SRBs, iron reducing and homoacetogen microbes. Their temperature is basically well fit, the thriving temperature well fit to underground hydrogen storage temperature. And if you look at the critical temperature at which they stop working, majority of these families stop working. I know that there are microbes that thrive in 300 degrees somewhere in the ocean. I'm not talking about that one. I'm talking about mainly indigenous microbes that we do see in underground formation that are suitable for hydrogen storage. You can see these temperatures are quite high in terms of temperature. We cannot inhibit the work of these microbes. If you look at the pressure, we can see the same same condition at the pressure will not stop them to work, because the pressure at which we are storing underground hydrogen we store hydrogen underground is not basically high enough to stop them to work. Salinity plays the same role, and you can see these microbes can live in high salinities. So there are microbes which are more suitable for these high salinity. In salt caverns that, if I'm not mistaken, in US, they report some contamination. In salt caverns, we have a swamp at the bottom, and that's fully saturated with, the brine there is fully saturated with salt. And it's surprising that the microbe still can live and thrive in such a high salinity environment. pH is a bit different. If you look at the optimum pH is around the neutral, but if you look at the critical pH is quite wide for some of these microbes. pH is a key parameter that you can stop one microbe and thrive the other microbe. I remember one of the pilots in Australia, basically, they manipulate the pH, or they try to work with the pH in a way that metagenesis thrive and SRB stop working, because they want to convert hydrogen to methane. In terms of the nutrition are available, mainly available, not basically as good as the laboratory experiment, but underground the nutrition are available. And as I mentioned earlier, inhibitors are there, but to my view, the inhibitors are not in a way that stop microbe to thrive, except for byproducts of the microbial activity like CO2 and H2S. Possibly the microbe themselves produce it, and then those byproducts will stop them to work. Something that I need to emphasize here is basically importance of the difference between laboratory oil and gas field and well consumption of the hydrogen by microbes. So in laboratory, we give them nutrition, a best environment, and as a result, microbes are thriving. But when it goes to actual field and the wellbore, these not as bad as what we see in terms of hydrogen consumption by microbes, and that's really requires a caution using the laboratory result for the old field. So the laboratory result is absolutely worst case scenario. Okay, coming back to contamination and conversion hydrogen, microbial activity are the main concern. Still, we need to do a lot of the research. You can see the risk of them are quite high. This will happen to majority of the cases. We need to have a very good view of how these microbes may react in particular site that we want to store hydrogen. Cushion gas can be a problem. If you use hydrogen as a cushion gas, there shouldn't be much of the problem. But if you use nitrogen, still we don't have the problem. But if you use, let's say, methane or CO2 for cushion gas, possibly people don't want to do it, but let's say if you store hydrogen in depleted gas reservoir, you already have methane and CO2 there. So not even in the form of the cushion gas, in terms of the mixing, that create a lot of problems. Okay, geochemical reaction again is marked low to medium here. Again, I emphasize on what I mentioned earlier in terms of the geochemical reaction. I'm not concerned about carbonate much. This carbonate will not do much of the reaction. Mineral like siderite, pyrite, those are the iron bearing, and possibly those are causing some problem. As I mentioned, for the majority of these carbonate, we really need a hydrothermal condition to activate the geochemical reaction. I'm not saying geochemical reaction will not happen, because when it gets combined with microbes, there are huge possibility for them to be catalyzed by microbe and proceed. Finally, we talk about storage performance. So here we talk about injectivity, trapping, and equation of the state. So for those parameters, we talk about permeability, porosity, connectivity, and many other aspects for the injection. In terms of the trapping, we need to look at wettability, capillary pressure, adsorption, desorption, and solubility. For equation of the state, I will explain later. And unfortunately, to best of my knowledge, we don't have a solid equation of state to model these underground hydrogen storage. People are using Ping-Robinson and other ones, modify Ping-Robinson, but to my view is not yet solid and not yet mature enough. So these are some of the experimental work for hydrogen performance, which I don't want to go through one by one, and I just put it here for your knowledge, and we can go and refer to them later on. And this is the performance assessment. Hydrogen ejectivity can be a concern when it comes to permeability, porosity, and connectivity. So we need to distinguish this concern when we are dealing with depleted gas reservoir on aquifer. In aquifer, we don't have a solid view of this parameter all around the aquifer. So, but in depleted gas reservoir, we've been producing from that reservoir maybe for 20, 30, 50 years, and we have a very good history of data which helps us. So for underground hydrogen storage, these parameters can be problematic, but for depleted gas reservoir, we know enough from the reservoir, but for aquifer, we don't necessarily know enough. And that can be a problem. When we go to trapping, mainly it doesn't have much of the problem, hydrogen trapping. The only thing which I want to emphasize here is angle of anticline, which we mark it as a medium. So let's say if you have a steeper angle of anticline or the trap structure of the hydrogen underground, it helps us to have lesser and lesser contact with hydrogen, with brine, with the rock, with the trap, and that reduces the chance of the contamination. So if it's steeper sort of storage is better for the storage. As I mentioned, equation of state can be a problem. We are not, I'm not aware of a very good solid equation of a state, especially when it gets mixed with the other gases, which does exist underground for, especially for underground hydrogen storage. That is a matter of the concern. Okay, there are not many economic assessment, and you might seen this economic assessment for Sandia National Laboratories. So they try to compare salt caverns, depleted gas reservoir, hard rock, and aquifer in a form of saying that which one is cheaper to store hydrogen. I don't want to go to every single details of the input of their model, but finally, this is the final result. It shows that depleted oil and gas reservoirs are cheaper in comparison to the other three techniques or three locations for storing hydrogen. But if you look at the result, you can see, for example, the difference between the salt cavern and depleted oil reservoir is because of the cavern mining. In here, we do have all of the infrastructure, but it assumes that all of the wells are suitable. It assumes that the pipes and the surface structure at the surface are suitable for hydrogen storage, which is not necessarily the case. So I do want to say this is a bad assessment, is one of the only ones which are available, but I'm saying still this assessment requires some attention when you want to be generalized. If we compare, let's say, depleted oil and gas reservoir compared to hard rock, you can see the compression and cushion gas price is the same. The one which really makes it very expensive is cavern mining. So putting everything together, you can see the compression and cushion gas cost is the same for all of them. And that basically makes the biggest capital cost for that particular volume of the storage. The rest comes from the infrastructure and site characterization. So if you have a very good infrastructure in your depleted gas reservoir, that makes it very good candidate for hydrogen storage. Okay, in the second part of the presentation, I want to describe some of our activities around hydrogen storage. Here we talk about looking at microstructure, some flooding, some aging, some analytics of the rocks that we are dealing, a bit of geomechanics and numerical modeling. And finally, I'll talk about some of the microbial tests that we've done. Okay, before we go forward, I want to share some of the experience we had, and possibly this is one of the good things you need to consider if you want to start testing hydrogen. So these graphs, sorry, I forgot to put the reference, shows at high temperature what is the permeability of different solids for the hydrogen. You can see stainless steel are here. It's still very good if you compare it with aluminum oxide, let's say in the form of sapphire. It's very different. Many order of magnitude is different, but in order to make a core holder out of sapphire, you need to use a fortune, and plus it might not even work. So when we saw these data at the beginning of doing this test, we decided to go and do things with stainless steel 316, and it becomes a kind of a standard material for doing the test for the purpose of underground hydrogen storage, because underground hydrogen storage, you are not dealing with extremely high pressure and temperature. So that makes 316 a very good candidate. So we try to use off-the-shelf material. So in order to have an aging cell, we basically use 2-inch pipes, and the connection of 2-inch, it will with a reasonable price and with a reasonable time frame makes a confined environment to, for example, age 1.5-inch diameter core with hydrogen. Something that you need to be very careful, which we experience, and you need to make sure you are not experiencing the same problem, is when you get the supply from even the well-known supplier in this field, be very careful, because sometimes they don't have every single component in their inventory, and they outsource the basically the material. In our case, this pipe was outsourced from another company with the one which we approach, and we saw this material, the pipe, and these nuts and ferrules are not same quality. Nut and ferrule was made with original company, very good quality, but the pipe wasn't. So you need to be very careful. Ask your supplier to make sure every single component is manufactured by them. Plus, we are using a hydrogen generator instead of using the cylinder for hydrogen, because cylinder can, things can go wrong with the cylinder and you end up with huge amount of hydrogen in your laboratory. But if you use, for example, we use this type, but you can use many of the other types. The good point about this GNEBIS is basically it produces high pressure up to 10 megapascal of hydrogen on demand. We just produce enough of hydrogen when you need it, and when you stop electrolysis in this equipment, there is no flow of the hydrogen into your lab. Okay, going to some of the tests we've done some tests on Beria and Bandera. If you don't know, Bandera sandstone is high clay sandstone, and we start doing some of the tests on 2 bridge sample. This is gas storage site in northwest of Australia. So in comparison, you can see, for example, this chloride iron bearing clay, Bandera has a bit more. In terms of the other clay, Bandera has more. In terms of the quartz, Bandera has less. And as I mentioned, we are doing, currently we are doing some tests on these 12 bridge samples. If we look at surface, a specific surface area of them, we can see by aging this with hydrogen, this surface area is increasing. As I mentioned, we still working on some of the aspects of Bandera and 12 Okay, so some of the SEMs with interesting results. Just bear in mind, when we age this material with or without the brine or with fresh water, we haven't killed the bacteria. So sterilization haven't done. We basically, our hand might have the bacteria, which I think thousands of these bacteria does exist in every single centimeter of your skin, and plus we haven't sterilized things, so we don't know whether geochemical reaction was the one which made these changes, or basically bacteria involved, or both of them. So that's distinguish. We can't make those distinguish when we were basically analyze the result. Citrate gone organic material which does exist in our specimen, which basically came from the pad that we polished the surface for the SEM. That organic material gone. But we couldn't see any carbonate quartz and feldspar is going. As I mentioned, for carbonate quartz, for carbonate, we need hydrothermal condition plus 250 degrees centigrade, and we don't have methane or CO2, which you usually should see, or any of the cushion gas in this experiment. It's just only hydrogen, and makes it a bit difficult for generalization because in underground gas storage of depleted gases, gas reservoir, when you want to store hydrogen, you definitely end up with some of this material, which will definitely change the way geochemical reaction will go, even for the microbes. So as I mentioned, we saw some mineral, iron-rich mineral like siderite, vanishes during these tests. We cannot distinguish whether that triggers by microbe or geochemical reaction or both. And if both, we can't understand the sequence of it yet, and we don't know how far each of them contribute. Okay, we've done porosity test and permeability test. For porosity of Beria, we don't see much of the change, but in permeability in 2 months aging, here, this is 16% reduction in porosity. For Bandera, which is basically clay-rich mineral, you see that porosity is dropped in 2 months. That might be sign of the bacteria growth. but permeability dropped 23%. So again, here we are not sure the extent of microbe and geochemical reaction there. So from now on, what we want to do is basically heat up the sample and try to make sure all of the microbes are dead. And if we want to introduce microbe into our system, we want to have a very specific microbe chosen or consortium of the microbe chosen already to at least know who they are, and we can quantify before and after introduction of the hydrogen storage environment. Okay, we've done a bit of testing, geomechanical testing. This is the barrier before and barrier after hydrogen aging. And surprisingly, we can see the rock become weaker and become softer. So young moduli reduces, Poisson's ratio increases, and ultimate strength reduces. That's a bit of a strange things to happen, because if you really don't have much of the geochemical reactions happening, why the rock is weaker and softer? And just bear in mind that both of these tests has been done wet. So it's not the effect of being wet to make it softer and weaker. So that's something that we are investigating to know why actually this is happening. In terms of the core flooding, we usually use the system of the core flooding with NMR. This is the setup in CSIRO. With NMR, we use this setup. Collaboration with the CSIRO, we basically put PTF, shrinkable sleeve around the sample when we put it in. Problem with almost every single material is the hydrogen pass-through. PTF gives us the best result. It doesn't stop hydrogen to penetrate into confining liquid, but it retarded a bit. But if you use almost any kind of rubber sleeve, Y10s, they will not be able to stop hydrogen. So that's one of the main concern of NMR hydrogen research, because if the test goes beyond few hours, then you should expect some of this hydrogen going to your confinement. Okay, so we those tests, those sample barrier and band area were examined in terms of the waterfront velocity. Is basically waterfront velocity means that the front of water passing through the dry sample, how fast that moves with single injection rate. So we've done it with intact, 1 month aging with hydrogen, 2 months aging with hydrogen, and these are the results. Okay, so what we see with barrier is intact has fastest. When we have the dry aged with hydrogen, the dry sample aged with hydrogen for 1 month, then we have with brine 1 month, brine 2 months, fresh water hydrogen 1 month, and fresh water 2 months. You can see it constantly reduces, and we basically correlated with activity of the microbes, saying that in fresh water microbes are thriving better, and that's why we have less water wet condition in here, and the time basically let them to thrive more, and that's why it reduces by time as well. So it's quite consistent in the case of the barrier, but when we go to Bandera, it's very difficult to interpret. Intact rock velocity is here, and when we go to 1 month brine and 1 month fresh, you can see the wettability is in the favor of water wet. So it becomes more water wet, but when we go 2 months, it basically becomes less water wet, not only in comparison with the 1 month, in comparison to original condition as well. So that makes it very difficult to interpret. To our view, it's something with microbe and geochemical reaction. As if you remember, I mentioned the Bandera has lots of clay. We've done some tests basically with a flooding test with microcity. This is the result of one of our ambient hydrogen flooding. Hydrogen saturation at the end of drainage was 65%, at the end of imbibition was 41%, and the change was 24%. That 24%, the capillary number are very low, which makes it capillary dominated flow regime for the Gosford sample gives us a very good changes, tells us that 24% of these gas can be produced in laboratory work. But when we go to these tests, which basically all of them has been done in 1.5 inch diameter sample with NMR, we can see that the change between the drainage hydrogen saturation and imbibition hydrogen saturation is quite low. That triggers the point that we have relatively low hydrogen withdrawal recovery if we just focus on capillaries, which is around the in capillary dominated area. So not discuss dominated areas, we can see that thing. So it's a matter of concern for hydrogen recovery, but again, more research should be done to have a solid understanding around these phenomena. Okay, in terms of the microbe, we've done some tests, so it's still going process. Just I'll show 2 of these samples, which we done with Team Fahad University. We basically put a sample without bacteria and a quartz sample in, and another specimen with quartz sample nutrition. This one does have the nutrition, but no bacteria. This doesn't have any, does have the bacteria and nutrition and the quartz sample. After 21 days, we look at the sample, the one which has the nutrition and the quartz sample, no bacteria, doesn't have much of the change. The pH doesn't change much, but the one with bacteria, the color changes, tells that we are producing H2S and the pH drops, which is sign of some organic acids. When we've done the FTIR, we clearly see these organic acid and biomolecules does exist in the system at the surface of the quartz. So we choose quartz for this test to make sure, okay, we don't have any geochemical reactions. But in next one, we use basalt rock. So we heat up similar to quartz, we heat them up to kill all of the bacteria, put it in one container without bacteria, but with nutrition, the other one with bacteria and the nutrition. And we age it for 21 days again. We've done SCM, we've done FTIR, and we done the contact angle. And surprisingly, what we saw is basically, again, biomolecules are producing. The reason we choose basalt in this case, because we want to see if there is a synergy between the microbe activity and geochemical reactions. And that's an ongoing process. We could be able to see the microbes growing and thriving in the surface of the basalt. And the result again shows the pH is dropping, means that bacteria's activity are happening. And I think the comparison of these 2 works are underway. So possibly in near future, I could talk about how this synergy between the microbes and geochemical reaction may occur in underground hydrogen stations, specifically just for basalt rock, which should be considered a kind of reactive rock. Okay. At the beginning of doing research, everyone was concerned about the cement, whether the cement will react with hydrogen or not. You know that typical Portland cement is being used for oil and gas cementing job, or consists of these 4 material. So we designated a standard name of C3S, C2S, C3A, and C4AF. So if you look at the different class of these cement that are being used in oil and gas industry, you can see C4AF, which is the only one which is iron bearing, has some iron in it, is iron bearing material, does exist in all of them. So if we look at these components in all of these cement classes, you basically can see quite consistent sort of the content for all of them. But we've done some geochemical reaction. I don't bring the models and K values here, but this is the before hydration. If you hydrate it with brown, you end up with this configuration. if you make hydrogen in contact with that brine for a specific period of the time, you can see basically not much of the changes are happening. If you compare it with methane, you can see typical methane wells are quite different to original hydrated cement because the reaction that happens. And if you look at with CCS case, it's completely different. So to our view, geochemical reaction results show that hydrogen and cement reaction is not a matter of concern. The concern is mainly coming from the fracture of this cement. You know that cementing jobs are not perfect. What they are really caring when they are doing the cementing is basically the shear strength, very low shear strength, and there are tons of problems may happen. As I mentioned earlier, the source of rock integrity problem in oil and gas and storage are well around the problems of the well. So that might be a problem. If you remember, I talked about the water saturation and diffusivity of the hydrogen in water. So if our cements with the crack are filled with the water, that can be a very good barrier for hydrogen to further migrate through the cements. That's some area of the research. We've done some tests on class G cement under 1400 PSI, 75 degree and 125 days. And we've done some dynamic tests, sound velocity VP and VS, and we calculate Poisson's ratio and dynamic elastic moduli. You can't see much of the changes happening in the cement. And we've done macrocity on those samples. Again, we couldn't see much of the changes happening. So we can wrap up that saying that most possibly the cement will not react in a way that people were concerned with hydrogen. So cement is safe. Again, the problem with the cement is through the fracture. You know that hydration of the cement in the exothermic and produce a lot of heat, and that heat will cause the cracks in the cement. Okay, finally, my last slide is about an integrated approach. This is the work that we've done with Kyushu University with Professor Sogai and Mr. Safari, the PhD student. The reason I bring it here is, if you remember at very early stage of this presentation, I mentioned about infrastructure and mentioned about geography, how that geography will affect the success of any of these underground hydrogen storage. In this work, what Alireza basically did is he did a very comprehensive literature review for 106 oil and gas fields in 4 provinces of the in Japan, and then made a very nice screening tools to value pros and cons of these gas fields, and then finally choose 8 of these gas field. I can give you the example of this screening tool. Basically, if it's really deep, it's not suitable for oil and gas because compression of the hydrogen going to be huge and the temperature going to be high. So if we really go below 2 kilometers, maybe in some literature they mention about 3 kilometers, but nothing deeper than that. So 2 kilometers to me is for depleted oil and gas reservoir, and 1 kilometer is for salt caverns. So you really don't want to increase the temperature and go deeper because deeper, higher pressure and higher diffusivity. So these are many other factors which actually plays important role in underground hydrogen storage. You need to look at the potential for renewable. So for both wind and the solar, when you look at the case, you need to look at the infrastructure. For example, in this case, we want to see how far is this storage to the hub of the population. I think you don't run out of the population when you talk about the Japan because it's quite dense in terms of the population. But again, you want to have the proper infrastructure. We look at the LNG ports that, again, Japan has many of these LNG import ports, which makes it suitable for if you want to convert them to hydrogen import ports. And finally, you shouldn't just look at the, let's say, injection and withdrawal performance. You need to look beyond that one. In this particular research, we look at the volumetric reservoir and water-derived reservoir, and we could see that volumetric gas, depleted gas reservoir are very good for hydrogen storage. And then we look at the performance of how this hydrogen being used later on for fuel cell or burning to produce the same amount of electricity. And again, the result here shows that fuel cells and volumetric reservoir are the best combination to keep more than 50% of the energy value of this hydrogen. Thank you very much for the opportunity you gave me for this presentation. And I don't know whether we have any Q&A session here now.
Thank you very much for your very, very interesting presentation, Mohammad Sarmadivaleh Sensei. Thank you very much. So now we will move to Q&A session. Do you have any questions or comments? Already we received 2 questions from Lian Sensei. Yes, we have 2 questions from Lian Sensei. Lian Sensei, please turn on your microphone and please ask question.
Okay, I think there are.
First question is the cushion gas injected in purpose for improving the hydrogen storage?
Yeah. So you know, if you look at any underground hydrogen storage, you need to keep a minimum pressure there. That's a volume at which and pressure at which the whole concept works. So you need to keep that pressure. That cushion gas must be there. Let's say if you have a very active water leg, which basically when you withdraw hydrogen or any other stored gas, the water comes and occupies the place and keep the pressure. You don't really need much of the cushion gas. But if you don't have it, in the case of volumetric underground gas storage, any form, you need to keep a mass of material there to basically keep that pressure. Otherwise, you cannot drop the pressure of the reservoir for geomechanical aspects or many other aspects and operational aspects. So the pressure cannot drop to beyond a certain value. That's the main reason for the cushion gas. So in gas storage, methane gas storage, these cushion gas are usually the same as the methane. But when it comes to hydrogen storage, there are other things that people are considering for the cushion gas. First of all, they really want to separate between the bottom of the reservoir, which is usually water, and the hydrogen. So if you put something in between, and if you put anything there is heavier than hydrogen. So let's say if you put nitrogen in between, it makes not only keep the pressure when you withdraw the hydrogen, but also make a barrier between your hydrogen and the water. So that's in hydrogen storage, cushion gas plays different roles. So the reason we have the cushion gas for hydrogen storage is to keep minimum pressure, which is required for operation and safety of the storage. And second, to make a barrier between the actual hydrogen and the remaining things at the bottom of the reservoir, which are usually water-bearing formations. Again, I should say that people are proposing to use hydrogen as a cushion gas, means that keep some of the hydrogen there and never produce it, and that work as a cushion gas, which is possible as well.
Oh, thank you very much. Yeah, I thought it's reduce the density difference between gas and water to increase the storage efficiency.
You know, if, storage efficiency, you need to keep the pressure there. Let's say in case of the volumetric gas reservoir, you cannot just produce all of the gas out. So it's operationally impossible. So you need to keep that pressure. Cushion gas provide that pressure and volume. But in terms of the hydrogen, cushion gas makes barrier as well. In addition to keeping that spring, that pressure there, makes the barrier if the cushion gas is not hydrogen.
Yeah, thank you very much. Yeah, my second question is, so in your, I don't know which slide you show several sandstone. So I noticed there is one called tubriki. So tubriki is a depleted gas reservoir. So my question is this tubriki gas reservoir going to be developed at the hydrogen storage site?
Okay. I'm trying to find, if I can find basically the slide which I had. Yep, this one. Oops. Can you see this slide?
Yes.
Yep. Basically, this is a slide I skipped. Tubrigi is here, okay, and is near to the pipeline. It used to be a gas-producing reservoir. Good point about this tubrigi is very shallow and very clean in terms of the sand. Now they are using it as a methane gas storage. But there are proposals with operator of this plant, which they may consider having it as a hydrogen storage. So if look at the position, where is it in terms of where is in the map? And if I go back to this map, which is potential for hydrogen in Australia, you can see tubrigi are in not far from this area. This is a good potential and possibly one of the multi-billion-dollar projects of hydrogen. In addition, there are so many of the mines which are try to be carbon neutral in these areas. And there are a lot of oil and gas activity going around here and going around here. So infrastructure is there. So if you look at the infrastructure, if you look at the existing customer like the mines, existing ports and existing facility for export LNG all together, so it makes tubrigi. I have to again go out because sorry, I need to find this slide again. Yes. Makes tubrigi a very good case for hydrogen storage, but is not yet a hydrogen storage site.
Yeah, because tubriki is quite close to the port. So,
yes,
for example, it can be used for export. Yeah. Anyway.
Yes. You know, the port is one aspect, pipeline is another aspect, because let's say at the beginning of hydrogen storage, you may want to have the blended gas. So you put hydrogen into your methane flow because you are not producing that much hydrogen. So it's near to pipeline, near to road, near to port, near to port terminals of the LNG, near to consumption sites like mines. So that makes it very good candidate for underground hydrogen storage. And it's not very deep. And the temperature is not high. If I'm not mistaken, between 30 to 40 is the temperature. So it makes it very good case. And plus it's clean sandstone.
Thank you so much.
Welcome.
Thank you very much for question, the answer said. Thank you. Any other question? If you have a question, please use raise a hand or type your question in the Q&A box on a Zoom window. Any question? Yes. Dr. Amirul Islam-san, please.
Yes, can you hear me?
Yes, I can hear you. Thank you.
Okay, thank you. The presentation was very nice and it was very clear to understand. And I have some questions, like two questions. One is you mentioned about two materials, which are Beria and Bandera. And I saw in the slide, yeah, this one, yes. So this surface area, 2 meters square per gram or 3 meters square per gram. So it's very small. Actually, we produce activated carbon and the surface area is over 1,000 and it can be about 3,000 also. So do you think that carbon has more potential to store hydrogen than this type of rocks or materials?
Okay, so you need to look at the scale you want to store it. Unfortunately, here, when I was discussing the different ways at the very start of my presentation here to compare them, let's say this slide, I haven't had the chance to look at solid state storage, battery, and the rest. Okay. So
Okay.
for example, if you look at the batteries are by no means in a terawatt scale. And the rest of surface storage are very valid and useful techniques, but are not able to address the way that it's supposed to be addressed in national or international scale. So I haven't had that calculation, but I would be very interested to see if we want to store it in solid state, 100 terawatts of hydrogen storage, how much of the volume of the carbon activated carbon do we need? To my view, it's gonna be tremendous.
Yes.
So activated carbon cannot basically address national or international scale. To my view, sorry, my knowledge in that field is very limited, but it has its own applications in many other hydrogen supply things. So when we talk about this one, underground hydrogen storage, you really need to have it in beyond gigawatt hours or around terawatt hours of storage to make it something good if you really want to go underground. Beyond that huge numbers, there are many other ways to store energy, including storing in solid state.
Okay, understand. And I have one more question, just simple one. So for the hydrogen storage, you need to give a very high pressure, and that high pressure producing requires a lot of energy. So do you think that that much energy or that much money is okay to spend just for hydrogen storage, or just make it and put it in a cylinder and sell it?
Okay, so let's say if you want to address 6% of Australian annual energy in form of hydrogen, so you need 341,000 of these tanks, and these tanks are not small. So when we talk about this scale, surface quickly goes away. So it doesn't mean that, let's say, if we have hydrogen fuel station, we need to use underground hydrogen storage. Do you get my point? Yes. So hydrogen fueling station, the techniques you are mentioning is very valid. So I'm not saying those techniques have no use in the future. Definitely they do have their own use for the scale. But when you really go to terawatt hours scale, none of them can address what we need. I can give you another example. Let's say the amount of LNG which is going around is massive.
Yes.
So if you really want to have those LNG methane stored at the surface, nothing works, because let's say Australia, Qatar producing a lot of this LNG during the summer. When this is a summer in Northern Hemisphere, Japan, South Korea, China, Europe doesn't consume a lot of methane. What they do, they make it in form of hydrogen and they store it in many, there are many gas storage in Europe. They store it underground, and during the winter, they use it. So if you want to store that volume of LNG at the surface, you need to just use almost all of the land in Europe. And it's not safe.
Yes. I understand. Thank you very much.
You're welcome.
Thank you very much for question, I²CNER Sensei. Thank you. Any other question? If no, I'd like to ask one question. Could you show me a slide 27? 27 slide. Sorry, 27. Yes. You are now showing the cost for hydrogen storage of each geological construction, such as sort of cavern and depleted oil and gas reservoir aquifer. How are the costs decided?
Okay, so we contact, these are the input to the models. So these are all into the model. So basically, they decide about the pressure, the volume, temperature, well depth, or everything. So I haven't gone through every details of this one. If I'm not mistaken, our postdoc Limping basically contact them, and they told him some of these data are confidential. They didn't provide some of these data, but again, what I want to mention here is this is just a simple comparison, and again, it should be used with a lot of caution, because this model is not good to talk generally about the comparisons. So again, that's why I emphasize that there is no cost for depleted oil and gas reservoir, almost not much of the cost for infrastructure, which is not true. So oil and gas been produced for 20, 50, 60 years, and all of these pipelines are rusted or aged. That has to be replaced. Legacy wells, old wells have a lot of problems. Underground completion might need to be replaced. Some wells must be abandoned properly, which unfortunately is not the case in oil and gas. We have many orphan wells which left by the companies. So this is just to compare, to have some comparisons, and to my view, shouldn't be generalized, but very good lines and guidelines. And you know, the other things is there is no cost of production here. So let's say cost of production in, let's say in, I'm not that much familiar with other countries. Let's say in Japan, there might be enough water available in a fresh form from the rivers, but in Australia, we don't have it. So when we talk about hydrogen production, green hydrogen production, it means that basically we desalinize the water from the ocean, and that's extremely costly. And then use it to electrolyze, which efficiency will kill this one, and make the hydrogen. Let's say if you want to export it in liquid form, again, huge amount of liquefaction, or as other friends mentioned, compression is there. So the efficiency is still a very big factor for all of these conversion that we do have.
Okay, thank you. I understand. And sorry, one small question. You had an experiment. Thank you very much. You had an experiment of cultivation of sulfate-reducing bacteria, and usually sulfate-reducing bacteria require organic matter such as organic acid for their growth. So in your experiment,
that's what we call nutrition.
Yes, this one. Yes. Did you add any organic matter in the culture solution, culture medium?
Yes, basically what we've done is nutrition. In this, I think I forgot to put the papers here. One of them with this, the paper related to this has been published already, so I should almost have put this paper there. Okay. There is a nutrition, and we know that this organic material, when they come into contact with rocks, quartz, they might age the rock and change the vitality. We are aware of that one, but that was the reason we had two batch. One batch was quartz with nutrition, no bacteria. The other one was quartz with nutrition and with bacteria, because we need to have the control to check whether what is pure nutrition effect. I know why you are asking this question, but we've done that one. And this one, after 21 days, the pH dropped slightly from the original one, but no bacterial growth because the color hasn't changed. But this one, bacteria grows and the pH dropped a lot. So that's how basically we try to subtract the only effect of bacteria. And especially that's very important when you do the contact angle, because if you age the rock without bacteria, you still change the contact angle.
Okay, I understand. Thank you very much. Any question? No. Okay. Yes. So it's now at 11:55 in Japan. So unfortunately, the time is coming. So I would like to close today's seminar. To Dr. Mohammad Sarmadivaleh-san, thank you very much for your interesting presentation today. Thank you. Thank you very much.
Thank you very much for having me here.
Thank you. Thank you very much for joining this seminar today. I'd like to close this seminar. Thank you very much for your joining.
Thank you.
Mohammad-san, thank you. Thank you very much.